If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay student, welcome you all to this new lecture in GATE series for power system. So today we will be solving again 5 questions, question number 6, 7, 8, 9 and then 10. Okay, then let's try to solve these questions. Okay student, in question number 6 what they are asking, for a 500 Hz frequency excitation, a 50 km short power line will be modeled as. Now short transmission line medium you might have studied with respect to length. Up to this much length is short, up to this much is medium, up to this much is excitation. A long line. But the actual idea is how you are taking consideration why these lengths are coming. If your length is very high, then you cannot ignore the effect of capacitance. That means the line is divided actually not on the basis of length, it is actually on the basis of effect of capacitance. If it is very high line, then effect capacitance length will be effect will be very high. Then we cannot neglect it. We have to take it distributed parameters as it is. If it is a medium enough, then also we are considering, but with a lumped parameter either pi or t. In short, the effect of capacitance is small, so that's why we take it as a small for 50 km line around that. So the effect is small, but that is for normal 50 Hz supply. But if we apply it 500 Hz, 50 km line length will look like a 500 km line length, because this frequency you are increasing it very high. So as you are increasing your frequency is very high, so you cannot neglect the effect of capacitance now. So because of that, your 50 km long line will be treated as a long line, because you have increased it 500 Hz. So 50 will look like a 500 km. For 50 Hz it will look 500 km. For equilateral spacing of conductor of an untransposed three-phase line. So it is untransposed. You know, transposition is done to strike a balance between the voltages at the receiving end, and with the transposition also there is a less interference in the line communication. So you will get a unbalanced receiving end voltage and a communication interface. That is your option D, unbalanced and communication. Here it is balanced, no. Unbalanced, no. Communication, no. Balanced, no. So it is unbalanced receiving end voltage and communication interference. Here L will be same, but if you are spacing it equilateral spacing, your L will be same, that is okay, but your C will be different. You can see if you are making it in a triangular format, so the distance from the ground is different. Here it is same, but here it is different. So you will not get a similar C in all these three lines, because this is your ground and the lines are going like this. So because it is C is here different, you will get a different voltage in the receiving end. L is same because the gaps are same. Now if you come to 8, a 220 kV 20 km long three-phase transmission line has following parameters. Its charging current. Okay, so its correct charging current means only the charging current that is flowing through the C. That means you are not giving any load, suppose. So what is my VSIS model? So that was my VSIS, AVR plus BIR, ABC, VR plus DIR. That was the model. Now suppose your receiving end current, this is your sending end VSIS, and your receiving end, this is VR and IR. Suppose there is no load, so IR is 0 suppose. So all the current that is flowing through IS, that is nothing but the charging current, which is charging this capacitance. There are infinite capacitance. Small capacitors are connected, distributed all along the line. So these capacitors are charging. So that is the charging current. So your IS will be equal to C into VR. What is your C? C they have given is 0.5 into 10 to the power minus 4 at an angle of 90 multiplied by VR. What is your VR? 220 km long. This is always receiving end, 220 kV if they mention. That means you are getting, the line is at 220, that means you are supposed to get 220 kV at the end. And this is always per phase. So you divide it by √3. So per phase if you are getting it, because they are asking you per phase, so 220 kV, if nothing is mentioned it is line, so divide by √3 will give you per phase. So if you solve it, it is 11 by √3, that is your option A. Now if you come to 9, for a single phase overhead line having a solid copper conductor diameter this spaced this much, the inductance in millihenry per kilometer. This inductance you know, L is equal to, we know total inductance, but here in the option it is divided internal external, but no need to worry. You apply the total inductance, then you see which one is satisfying. This was Ln GMD. If it is space between the centers, they are solid copper diameters, two single phase, so the distance between them is 60 only. because there is only 2, so one distance will come, and divided by GMT 0.77 r dash, it was 0.7788 into r dash, diameter is so it is r 0.5 into 10 to the power minus 2. Now you calculate and check with the option which option satisfies this one, or you can segregate also. You take this part of 0.778 different, so that will come. Actually this is 60 by 0.5 they are talking about, and that 0.778 you take it, log this minus this, so 0.777 if you take, it will come 0.05. So it will come option C. Actually this unit is Henry per meter, so you have to change it to millihenry per kilometer, then you have to check with which option it is satisfying. So if you check, you will find it is satisfying with C. Now if you come to 10, the corona losses are minimized when conductor size is reduced. No, you need a greater. Why corona occurs? Because its electric stress per unit area becomes very high, so that the air surrounding it becomes ionized. So your conductor size is reduced, then means your surface area will get reduced, then the voltage per area will get increased now, because you are reducing the area. So it is not the smoothness of conductor is reduced. No, we need a smooth conductor. If there is a rough spots, corona will be higher, because at that spots your electric stress will be more. It will not be uniformly distributed, all the electric stress around the conductor. The sharp points are provided in the line hardware. It is not okay, because it is, you can see it is contradictory to this one. It is the same thing. Smoothness reducing, giving sharp points will also increase the electric stress. Current density in the conductor is reduced. Yes, if you are reducing the current density, that means you are increasing the area of the conductor, surface area. If you increase the surface area, then its lateral surface area, outside periphery area will also increase. So electric stress means, suppose if it is the conductor, you are increasing this cross sectional area. If you are increasing this cross sectional area, then this outer surface will also increase. So your electric stress per surface will get reduced, so the chances of ionization of air around it will get reduced, so corona will be getting reduced. So that is your option D. If you like the video, then press the like button and please give your valuable comments in the comment section.